In section 2.8, we'll look at Lewis acids and bases now. So the rest of the chapter, we've pretty much been looking at Bronsted-Lowry acids and bases. Now we're going to look at Lewis acids and bases, which uses a different definition. And then later on in this section, we'll learn that there's a different terminology that we'll use of electrophiles and nucleophiles most of the time in organic chemistry, and we'll save Lewis acids and bases for only a couple of very specific situations. So first of all, let's look at the definition. A Lewis acid is now an electron pair acceptor. So with Bronsted-Lowry, we're all concerned with a proton. With Lewis, now we're looking at electron pairs. And that makes a Lewis base an electron pair donor. So Lewis acids, as compared to Bronsted-Lowry, do not have to have a proton anymore. So that makes them quite different. However, a Lewis base is really the same as a Bronsted-Lowry base, because both of them had to have an available electron pair. So let's look at a couple of examples. So I can take boron trifluoride, boron has 3 electrons, each fluoride has 7, so there's a full octet around each of our fluorides. And since fluoride has 7 valence electrons and these have 7, they're neutral. Boron has 3 valence electrons, this one has 3, it's neutral. However, this boron does not have an octet. If I look at the electrons around it, there's only 2, 4, 6 electrons around that boron, so there's no octet. That means that this boron will be an electron pair acceptor. Or, another way to say it is it will be a Lewis acid. You can do a similar thing with aluminum and draw an aluminum compound. As aluminum is right under boron on the periodic table, it also has 3 electrons, and you can see the same thing is going to happen here. There's no octet on that aluminum, there's only 6 electrons around it, and it's also then going to be an electron pair acceptor and a Lewis acid. So what do the reactions look like? So let's do a reaction now. Now if I look at these two molecules, the BF3, or the boron trifluoride, this is going to be my Lewis acid because it doesn't have an octet. Then the oxygen over here will be my Lewis base because it has lone pairs of electrons that can react. So anytime we look at reactions in organic chemistry, one of the most important things to look at is who has electrons and who wants them. So this oxygen is the one that has electrons, this boron is the atom that wants them, so the electrons will flow from the oxygen to the boron to make a complex. There's the new bond between boron and oxygen. The boron then has 3 fluorines on it. The oxygen has 2 hydrogens on it. Now if we want to look at formal charge, we can look at the oxygen first. So the oxygen has 1 lone pair. So there are 5 electrons that belong to oxygen in this molecule. And oxygen has 6 valence electrons, so this has a +1 charge. And boron, there are 1, 2, 3, 4 electrons that belong to boron in this complex. So boron has a -1 charge. So electrons moved from the species that has electrons to the species that wants them. Wants electrons. So when we talk about this in organic chemistry, what we'll say, instead of talking about Lewis acids and Lewis bases most of the time, for Lewis acid, this will be an electrophile. Phile comes from philos, which is a Greek word for love. So electron lover, it wants electrons, something that wants electrons. And the Lewis base is something that we'll call a nucleophile. So this has electrons that want a nucleus to belong to, better than the one that they're on now. So we have an electrophile and a nucleophile. That's the language I will be using throughout most of organic chemistry. Electrophiles are things that want electrons, nucleophiles are things that have electrons. And we'll save discussion of Lewis acids for a few specific cases. But these two are going to be very common throughout organic chemistry. We'll talk about electrophiles and nucleophiles in nearly every reaction that we look at.